Welcome to another lecture for Interactive Computer Graphics. Today, we are going to talk about lights and shadows. Our main topic actually is shadows, but it's really not possible to talk about shadows without lights, right? When I ask people like, what's a shadow? Oftentimes what I hear is something like the absence of light, which is, well, it makes sense, right? It's a reasonable description, but I would say it's the absence of light in the presence of light. There has to be light somewhere. So if there's no light in a room, are there any shadows? Probably not, right? So you got to have some light somewhere illuminating some things, but not certain parts of a scene, which is where we have shadows. So light and shadows basically go together. They cannot be really separated. So let's start with shadows. I'm going to talk about lights. We talked about lights before, but I'm going to talk about today the parts of the discussion regarding lights that we haven't really covered so far. But let's start with shadows. So let's say that I have this lovely object. Well, are there any shadows? Well, you could say maybe the back part over here is shadowed, but let me put a shadow down here. Oh, all right, so here's the shadow. So what does this shadow tell you when you look at it? It does a very important job, actually. Like it should create this illusion of a plane underneath the ball immediately. Like as soon as you see it, you're like, oh, there's a plane. The ball is on a plane, right? I'm not showing you that plane, but you can tell that it's there, right? Just because of the shadow. Another thing you can tell is probably where the light source is. This specular highlight on the ball is also giving a hint about the position of the light source, but also the shadow. Just by looking at the shadow, you can have a guess about where the light source is. Let's say it's somewhere here. All right, so that's where the light source is. Now, this is a very, very, very important effect. Very, very important effect. This is something that we would like to be able to compute properly. Very, very important. Let me show you why this is very important. I'm going to move this shadow. I'm just going to move this shadow and nothing else. Ready? I'm moving the shadow. Shadow is over there. Oh, what did I do? What happened? Oh, this ball is no longer touching this plane, right? It's just it floated. But I didn't move the ball. I didn't move the plane. I just moved the shadow. This is very, very important, right? So the shadows, they give us a very clear sense of how different things are oriented according to each other. So I have a sense of where this ball is in comparison to this plane just by looking at its shadow. Right? So it's a very, very, very good indication. Now, what happens if I remove it? If I get rid of the shadow? What do you see now? Like, where's the ball? Where's the plane? You can't even tell, can you? You look at this, you have no idea. They probably are not together. They're probably not, like the ball is probably not touching the plane. And if it is, there's something really wrong here, right? It just doesn't look right. It's very important to get this right. Okay, but the thing is, we've been doing things properly. We did some approximations, we did some simplifications, we used that simple shading model and whatnot, but we haven't been getting shadows in our renderings. So we've been using the rendering equation, right? The shadow should be here somewhere. This is the rendering equation after all. All right, so we used a simplified form of the rendering equation. We said light is not coming from all directions, it's coming from just one light source. If it's coming from one light source, this simplifies to this simpler form. This whole integral collapses into this form. So, but where's the shadow here? Oh, it's got to be somewhere, right? It cannot be nowhere. This is the rendering equation. It must include everything. It's hiding in here. The lighting term. Well, regardless of which object you're rendering, the ball or the player or whatever object you're rendering, the shadow is going to be hidden inside this lighting term. So let's take a look at this lighting term a little bit. So what is this? We've been saying, oh, this is just the light coming from the light source. What do we, well, we used just the light intensity for this, right? But actually, this is a little more complicated than that, this lighting term. This lighting term includes, there's a term that represents the light intensity and at that point, but also there's a visibility term. And when I'm going to multiply these two together, this visibility term tells me if the light can see that point at all. Because if the light cannot see that point, it's going to be in shadow. If the light can see that point, then it's not going to be in shadow, right? So this visibility term, you can think of this as like 1 minus shadow. If it's in shadow, if shadow is 1, visibility is going to be 0. If shadow is 0, no shadow, visibility is going to be 1, that the light is seeing the point, right? So, but we're going to get there. We're going to talk about shadows. But this is the way that we're going to be putting this into our rendering equation. All right. So let's take a look at this one first a little bit. Let's take a look at this intensity term just a little bit. All right. So this light intensity, yes, but when we talk about light intensity, we're actually talking about the light intensity at the point that we're shading. So oftentimes when people are writing the rendering equation, they use this simpler form where the light just directions. But actually, we compute the rendering equation at a point on a surface, right? Let's say like a point X on a surface. This is the point that we're shading. The surface normal and everything is defined. The material properties, dBRDF, everything is defined at that point X. So a more proper way a longer way of writing the rendering equation would include these x's in all of these terms. In all of the terms in the rendering equation would have these terms, right? So it is the light at that point coming from this direction. So this is the light that received the light intensity at x. This is the visibility at x, right? So we're going to look at that point x, and let's see how much light is coming, because you might assume that the light coming to that point X is just the light intensity, but that's not necessarily the case, because there's this concept of light attenuation, something that we haven't really talked about in this class. So let's talk about it. Let's talk about light attenuation before we get into shadows. What is light attenuation? So I'm pretty sure you're familiar with this. So when you look at some light source in the background over here, and it's illuminating this dark room, and there's a plate on the floor, and as you can see, the amount of illumination on the floor varies. It's not the same. Obviously, you get more light closer to the light source, much less light away from the light source, right? This is intuitively what we expect, because that's what happens in reality, and that's what we would like to see. So this is the concept of light attenuation. The intensity that you receive at a point depends on where that point is with respect to the light source. So if the light source is far, far away, we won't be receiving that much light. If the light source is close by, then we will be receiving a lot more light, right? So how can we incorporate this in our formulation? All right, so we said that this is our lighting equation, right? So this is the amount of light that's point X is receiving, and this is the visibility term. So let's take a look at this term. What is this? So we have been approximating this term as just the intensity of the light source, right? So the intensity parameter of the light source, whatever that is, that's what we've been using there. But it's actually just a little more complicated, just a tiny bit more complicated. A more proper way of writing this would be the light intensity times some attenuation. So this is the light intensity term. This is the property of the light source. And this is the attenuation function. I mean, there are ways to write this a bit more complicated, and it would be more suitable for more general light sources. But for the relatively simple light sources that we will be using in this course, this is a good way of writing the lighting equation. All right. So there's light intensity. This is the property of the light source. And there is there is an attenuation function. This attenuation function will determine what percentage of that light point X will be receiving. What percentage of the light coming from this light source the point X will be receiving. All right? So what is attenuation for a point light? So you must be familiar with this formulation. If I have a point light and I have an object receiving light from this point light at a certain distance d, then the attenuation function is going to be 1 over d squared. So the inverse square attenuation function is what we call it sometimes. 1 over d squared is going to tell us how much light intensity is scaling as we move away from the light source. But why is that? Actually, there are multiple ways of sort of deriving this formulation. The simplest one that's specifically for point light source is what I'm going to talk about. So if I have a point light source like this at a point, imagine that I put a sphere around this light source. Imagine I cover this light source with a sphere. Now, the interior of this sphere is going to capture all of the light that's coming out of this light source, right? So all of the light that's coming out of that light source will be captured by the interior surface of this sphere. Let's say that my illumination coming out of this point light source is isotropic. It's the same in all directions. So I'm getting the same illumination per area on the interior surface here. What happens if I make this sphere larger? If I enlarge this sphere, I'm still going to get the same amount of total light. But now this light is distributed onto a larger surface, right? Because it's distributed onto a larger surface, I'm going to be getting less light per unit area, right? So if the radius of this sphere is d, the distance from the light source, the surface area of the sphere can be written with the formula 4 pi d squared, 4 pi r squared, 4 pi d squared in this case, right? So this is the surface area of the sphere. And because of that, so see that the surface is enlarging by d squared. That's why as I enlarge this sphere, the amount of light that I'm going to be receiving per area on the sphere is going to decrease by 1 over d squared. All right, so this is the reason why we're getting this 1 over d squared attenuation with point light sources. All right, this is good. This is the right thing to do for point lights, but it's a little bit problematic. There's some practical problems with this. That is, d can be, if d is large, it's okay. This is going to go to 0. But if d is small, this is going to be too large at some point. All right, so and because as d goes to 0, this is going to go to infinity, and that's a little bit of a problem. Well, we have been living with this problem for so long in computer graphics. People came up with all sorts of different types of hacks to get around it. For example, you just add some constant value to the denominator here so that it never goes to infinity, but goes to some constant value. Or you make sure that if it's larger than some constant, you set it to a constant, you can just clamp it. So the people came up with all sorts of tricks. Last year at SIGGRAPH, I gave a talk on a different formulation for point lights. So the problem with this is related to the fact that this is a point light source. This is the correct attenuation function for a point light source. The problem is the fact that we're using point light sources at all. The light source has no size. And that's why we're getting this. If the light source had a size, we could get around it. So I came up with this simple modification of point light sources. Just add a radius. Turn it into some sort of like a spherical light source. Not quite a spherical light source, but yeah, think about it as a spherical light source, but it's still a point light source. Spherical light sources are a little more difficult to handle properly. Point light sources are very, very simple. That's why we like them in computer graphics a lot. But I want to add one thing from a spherical light source, just its radius. And when I add its radius to a point light source, this becomes a point light source. It's not a point anymore. It has a radius associated with it. And as this radius goes to 0, this radius parameter goes to 0, we're going to have the attenuation function of 1 over d squared as expected. So I came up with some derivation of how we could define an attenuation function for a point light source that has non-zero radius. A point light source with non-zero radius. That sounds really weird because a point is supposed to have 0 radius. Yeah, so it's not really a point light source. All right? It's kind of like a point, but not exactly. So I'm not going to go through this derivation. What I'm going to tell you is that if you're interested, I have my talk on that recorded. It's on my YouTube channel. You can listen to it. I think you guys have enough background to listen to that talk and get everything out of that. So if you're interested in how this thing works, please go ahead and watch that presentation. It's not very long, and it's quite detailed. But I'm going to show you the result. After some derivation, starting with the rendering equation and simplifying things, we end up with this sort of scary looking formula. It's not too scary though. In addition to this d squared and d terms, we also have this r squared terms. And here, what happens is that when r goes to 0, this actually goes to 1 over d squared. Now, it's not so easy to see that is the case just by looking at this formula. But if I rearrange the terms and write this formula like this, that becomes a bit easier to see. When r is 0, this r squared disappears, this r squared disappears, so I get d squared plus d squared, so 2 over 2d squared, that means 1 over d squared, right? And actually, this is if you ever want to implement something like this, this is the form that I would recommend, because this turns out to be numerically a bit more stable. So use this formula, not the previous one. Anyhow, if you want to find out how I came up with this, go and check out this this talk. It's on my YouTube channel. Right, so this was a point light source. What happens for an area light source? How do I define the attenuation for an area light source, a more general area light source? Well, this is not that easy. Not that easy because there are a lot of factors in here. I need to consider not just the distance to the light source, but I also need to consider the orientation of the light source, because it has an area now, it has a shape. And I need to consider the shape of the light source. I'm not thinking about shadows at this point. I'm assuming that I'm seeing all of the light source, right? From point X, I will be seeing all of the light source. But even that, like how much light is coming, and there's not a single light direction now, there are multiple light directions, right? So computing all that is not that easy. But turns out, you can actually do this analytically. So there's an excellent paper from SIGGRAPH 2016, and I would highly recommend that you check it out if you're interested in this. It's an excellent paper that tells you how you could compute area lights, not just light attenuation. So this basically real time. How would you compute area lights at real time using a closed form formulation? It's an excellent paper. I would highly recommend that you check it out. Actually, this would be a very, very nice project for your final project. So very nice topic for your final project. So I'm not going to tell you how it works. It's a little complicated. So I don't want to get into the details of it, but I would recommend that you check it out if you're interested in finding out how it works. So, but it can handle, I'm going to show you that it can handle these types of area lights, but it can also handle any type of polygonal lights, like a star-shaped light. That's fine. It also, the light source could have some texture to it, something like this. And this is all real time and analytical. It works really great. I would highly recommend it. All right, so this is everything that I wanted to talk about regarding lights. So light attenuation, in the case of area lights, is a bit more complicated, but we will be dealing with point lights and directional lights mostly, at least for the next project and the upcoming few more projects. So you can incorporate light attenuation to your projects if you like. That's not going to be a requirement though. Our main topic for this week and for our next project is going to be shadows. Shadows that's the part that's going to be important. So what I'm planning to do today regarding shadows is that we're going to talk about some shadow computation methods at a relatively high level. We're going to get into some details, but I'm not planning to talk about implementation details today. So I'm saving those for Thursday's lecture. On Thursday, we're going to talk about a particular shadow computation method, the one that we're going to be implementing, and I'm going to be talking about its details, how to implement it on the GPU. But today, we're just going to talk about them at a relatively high level, and we're going to see multiple shadow computation methods. All right, shadows. We have this lovely scene. Our ball is here, our plane is here, our light is over there. I know their positions, but I cannot see their positions because I don't have shadows right now. The problem that I'm trying to solve is, given a point X somewhere, let's say a point on the plane. Given a point on the plane, is this point in shadow? That's the question. We talked about visibility, right? So if this point is visible to the light source, that means it's not going to be in shadow. If the light can see that point, then it's not going to be in shadow. Or from this point, if I look up and if I can see the light source, that means that point is not going to be in shadow. That is, if I draw a line from this point to my point light source, if I draw a line, if that line does not intersect with anything, then this point is not going to be in shadow, right? But let's pick some other point. Let's pick this one. In this case, if I draw a line from this point to the light source, it's going through this sphere, right? It's going through this ball. So that means that this point will not be able to see the light source, so it is in shadow. All right? So this is what we're going to be computing. Now, the easiest way of computing this, the easiest way and probably the most versatile way of computing this would be using ray tracing. Yeah, ray tracing is a pretty good solution for a lot of rendering related problems, and shadows definitely included. So how can we do ray trace shadows? Fairly easy. With ray tracing, let's say we're rendering with ray tracing. This is my camera. For rendering, I'm just sending a ray through a pixel, and that ray went and hit this point that I'm interested in. That's why I want to shade this point. And from that point, I want to find out whether that point is in shadow. It's in shadow as compared to this light source. Okay? So what do? I just send another ray starting from that point towards the light source. To send another ray, we call this a shadow ray. So I send the shadow ray from this point towards the light source. If that shadow ray reaches the light source without intersecting with anything, then I'm going to say the light source is visible, the point is not in shadow. If that ray intersects with something before reaching the light source, I'm going to say, well, there's an object in between the point and the light source. That means the point cannot see the light source. That means it's in shadow. All right? That's the whole idea. It's fairly simple, relatively easy to implement. It's and a relatively general method too. So for a point light source, I can just send a ray, a shadow ray towards that point. If I have a directional light source, I just send a ray in the light direction. Right? So as long as I know the light direction, I can use ray trace shadows. What happens if I have more complicated light sources, like I have an area light? Because an area light will not have a single direction, but there's going to be a range of directions where the light will be coming from if I have an area light. in which case what we will do with ray tracing will be sampling. So we're going to be sampling different points on the area light. That's how we handle area lights with ray trace shadows. Right. So this is it. It's a very versatile method. It's a very easy method, and you can implement it. And when you implement it, just as I described, you will probably get something like, are you ready? Like this. Oh, wait, what happened? Nah, something got messed up. What? No, what's happening here? Do you see some tiny lines here? Something is a little messed up, right? What is happening? Why is it happening? Let's talk about that. So in this 2D cross section, I am sending a ray from my camera that hits this point on the plane, and then I'm sending a shadow ray, and by tracing that shadow ray, I will determine whether or not this point is in shadow. All good? All right. So what's happening? Let's zoom in to this point. Let's zoom in a little bit. Okay. Let's zoom in some more. Oh wait, what happened? Hey, this point is not on the plane anymore. Something I messed up. Let me tell you what happened here. Let me tell you what happened. We thought that this point was on the plane. But remember that we are dealing with finite precision floating point numbers. So it is possible that this point that's exactly on the plane cannot be represented with our floating point precision. Or it's also possible that the way that we're doing all this computation, we're going to have some minor floating point errors, and those errors accumulated, and the point that I calculated is going to be sort of off this plane. Now, if this point happens to be above the plane, I'm okay. It's not going to give me trouble. But if it is below the plane, what's going to happen is that when I send a shadow ray, that shadow ray will just hit this plane. Right? Shadow ray will be hitting this plane. So it's as if this point is shadowing itself, which is not good. Not good at all. That's definitely not what we want. But it's a very, very typical problem because we're always dealing with finite precision. We cannot have infinite precision. Even if we could, we don't want to. That would be way too expensive. So we're going to be dealing with finite precision floating point arithmetic. That means that, yeah, we're going to have this problem. So what do? Well, we incorporate that into our computation. And we say that, you know what, when I send a ray towards a light source and the ray just hits an object, hits something so close to its origin, I'm probably hitting the point that I'm supposed to be shading. Right? It's very likely that that's the point that I'm shading. So how about I ignore that? So how about I ignore any hit I find that is way too close to the ray origin? So that's one way of handling this. So what we're going to do is effectively, it's as if we're moving the ray origin up a bit. We're actually not necessarily moving the ray origin. We're just going to assume that any intersection in this range will be ignored. I'm only going to be interested in intersections beyond this point. Right? So what I'm going to do is I'm going to add some bias. This is what it's typically called. I'm going to add some bias, and with that bias, I'm going to ignore all intersections within this range. Now, there are different ways, different methods for adding bias. This is the most typical way of doing this. There are different ways also. You can add a constant bias. You can adjust this bias based on the ray direction and the surface normal. Instead of adding a bias, you can move this point above the surface a little bit, so you can more carefully compute this position and make sure that this point is always going to be above the plane. So there are different ways of handling the bias. The one that I really don't like is going to be sort of keeping score of this plane, keeping a note of this object and say, hey, if I'm hitting that object, I'm going to ignore that. That's not what I would recommend, because that's not necessarily what we want to do. Sometimes you would like that point to be able to cast shadow onto itself, that surface, if the surface is not planar. But in some cases that actually works. So that's another solution that could work in some cases. Right. So regardless of what we do, we're going to have to add some sort of bias, or we're going to have to make sure that this point that I'm trying to shade is not casting shadow onto itself. Right. So that's going to be a problem that I'm going to have to deal with. But if I do this properly, then I'm going to get these nice shadows with ray tracing, and everything will work out just fine. All right. So this is ray traced shadows. Of course, I'm presenting this in the context of ray tracing, like everything is ray traced, but I don't have to start with ray tracing here. Actually, it doesn't really matter what I start with. So the actual primary visibility could be computed using some other algorithm. It could be computed using rasterization. After I find the point that I'm going to be shading, that's when I can send a shadow ray and compute it using ray tracing. But if I'm going to be sending a shadow ray, that means that I have access to ray tracing. Now we have ray tracing capabilities in some latest GPUs. So it is possible to do that even in a fragment shader. Well, I shouldn't call it fragment shader because it's not supported in OpenGL, but it is supported in DirectX. And I shouldn't call it fragment shader because DirectX calls that pixel shader. So inside a pixel shader, I can actually send the shadow ray and compute shadows using ray tracing on the GPU. It's going to be relatively expensive though. Relatively expensive because ray tracing is not the cheapest way of computing shadows. It's not too expensive. Shadow rays are significantly cheaper than other types of rays because I'm not trying to find what this ray hits. I'm just asking if it hits anything, and I don't care what it is. When I send a shadow ray, I just care about this query of, is there something in between this point and the light source? Yes or no. I don't care what it is. If there's something, it's going to be in shadow. If there's not anything, then it's not going to be in shadow. So these types of rays are relatively cheaper to compute, but nonetheless, it is ray tracing. There's going to be some cost associated with it. And especially for real-time interactive rendering, you may or may not be able to afford that cost. So what we're going to do is that we're going to be talking about methods that are not going to be ray tracing only. Yes, ray tracing is a great solution, but it only works on some new high-end GPUs, and it has some costs. Even on those GPUs, you may or may not want to use ray tracing for computing shadows because it's not free, right? And we talked about this, right? Shadows are very, very important. We definitely need some other ways of computing shadows without ray tracing. We have been rendering stuff before we had ray tracing support. And when we were rendering stuff, we had shadows because without shadows, things really don't look right. They look really weird. We saw that a little bit ago. So we're going to talk about how we can handle shadows without ray tracing, without touching ray tracing at all. Okay, so let's assume that we have no access to ray tracing. We're doing rasterization. Remember rasterization? Yeah, that's what our GPU rendering pipeline is designed to do. All right, so we're doing rasterization. How am I doing rasterization? I get one triangle at a time, and for each triangle, I just compute its canonical view volume position. Basically, I project it onto the screen, and I shade it, right? I get the next triangle, and I project it on the screen, and I shade it. And while I'm shading this blue triangle, I don't know anything else. I don't know where the red triangle is. I don't know if there are any other triangles here. I may know where the light source is. I'm sending that information to my fragment shader, so I probably know where the light source is. But there's no way of checking if there's anything between a fragment here and the light source. The rasterization algorithm does not give me any way of asking that question. So what are we going to do? What we're going to do is going to be probably the most popular way of computing shadows today besides ray tracing. That's going to be shadow mapping. Very, very, very important topic. We're going to be implementing shadow mapping for our upcoming project. And our next lecture on Thursday is going to be devoted to shadow mapping and how to implement shadow mapping. But today what I'm going to do is I'm going to just give you an overview of shadow mapping. We're going to talk about shadow mapping at a high level. And on Thursday, we're going to talk about shadow mapping in a more detailed sense. Okay? So here's how it works. With shadow mapping, what I would like to determine is whether a point is visible from the light source. So if I were looking at this plane from the light source, I'm looking at the scene from the perspective of this light source, what would I see? If I can see that any point that I see from that light source will be visible to the light source, obviously, that means that it's going to receive light. Any point that I cannot see will not get light. That means it is going to be in shadow. So that's the whole concept of shadow mapping. So what we're going to do is that we're going to take this light source and we're going to replace it with a camera. All right? And I'm going to be rendering an image from this light camera. I render an image from this light camera. And everything that's visible on this image is going to be visible. That means that it's visible to the light source. That means that I will be able to see light on those points. So they're not going to be in shadow. Any point here that is not visible to the light source, that's not visible on this image, will be in shadow. So, but by looking at this, how can I tell if a point is visible or not? I mean, I only see the things that are visible here. What I'm sort of interested in finding out is things that are not necessarily visible, right? So like this point over here that I'm trying to shade, it's not over there, right? So what I'm going to do is that I'm going to check the corresponding position of this point on this shadow map, that point. So as you can see, that point is on the ball, it's not on the plane. So obviously, it's not visible to this point is not visible to the light source, but this point is visible to the light source, right? So that means that point is supposed to be in shadow. But how can I determine that? It's kind of hard to do it when you render an image like this. What we want to render is not this, but a depth map, the Z buffer. Remember we have a Z buffer when we're rendering with rasterization? Yeah, we're going to use that Z buffer. We're going to put it to good use. So we're going to render the image, but we only care about the Z buffer. We only care about the depth map. Depth meaning how far a point is, how far a fragment is from the camera. In this case, how far it is from the light source. So when I'm rendering with shadow mapping, what I'm going to do is that I'm going to first render this depth map image from my light source. If I have multiple light sources, I'm going to do that for each one of my light sources. After I'm done rendering that depth map, now I'm ready to render my final image using my actual camera. That's the camera that I want to use for my scene. And I'm going to be rendering that image. And for any fragment here, then I'm going to find the corresponding position of that fragment on my shadow map. So I'm going to take the position of the point that I'm shading, and I'm going to transform that position to a position on the light camera, and that will tell me where it is on this depth map. And I'm going to look at that depth value. And I'm going to look at that depth value stored in the depth map to how far this point is from the light source. Again, I'm going to look at the depth value here, the depth value at the corresponding point here. This is going to tell me how far that point is from the light source, right? That's what depth map tells me. And I'm also going to look at the distance from this point that I'm shading to the light source. And I'm going to compare the two. I have a depth value here recorded in the depth map. I have another depth value that I computed as the distance from the shaded point to the light source. Now, if the shaded point is further away from the light source than what I find on the depth map, that means it's a point that's behind something here. Right? Again, if this point, if the distance is larger than the distance I find in the depth map, that means that the point is going to be in shadow. If it's close to it or the same, then I'm going to say it's not in shadow. Again, we're going to have bias related issues here that we're going to have to consider. Another thing that we're going to have to consider is going to be the shadow map resolution. So this is going to be an image that I will be rendering. We're going to also be considering filtering, how we can do proper shadow map filtering, all that stuff we're going to talk about next time. But today I want to just give you an overview of shadow mapping, and this is what it is. Now, one problem with shadow mapping is going to be related to the shadow resolution. So if I have, let's say, a scene like this, and you have nice shadow down here, oftentimes what happens is that I may not have enough shadow map resolution. Like I can, instead of getting a nice looking image like this, I might get something that looks like this. Not this, but this. It's kind of pixelated, not looking very good. The reason is that not necessarily that I'm having a very low resolution shadow map. My shadow map might be quite high resolution actually, but maybe my light source is far, far, far away. And this is not atypical. It happens. Sometimes we put light sources that are kind of far because, I don't know, maybe it's supposed to represent the sunlight, or maybe I'm in a large environment where I have to have some strong light coming from a far light source. That can happen. So if I try to render the shadow map from a light source that is relatively far, the depth map that I get might look like something like this. This might be relatively high resolution, but as you can see, I don't have that many pixels, or pixels I should say, on my depth map that corresponds to this area, to this pawn here. Yeah, so that's going to be the problem. So even if I have a high resolution depth map, it may not be high resolution enough if the light source is sufficiently far and it's covering a relatively large area. Now there's a brilliant solution to this. Using a method called perspective shadow maps. Now, perspective shadow maps, take a look at this. This image is going to change and the shadow is going to be changing. With perspective shadow maps, I get a depth map that looks like this. So with regular shadow maps, this is the depth map I'm getting. With perspective shadow maps, this is the paper explaining the perspective shadow maps. This is the depth map that I'm getting. It's much better. And the shadow map I'm getting is much better. And the reason why this is much better is that the depth map is kind of looking like my camera view, right? I mean, look at this. They kind of match. If I look at this regular depth map, this is definitely not the camera view, right? This is the light view. It looks nothing like the camera view. But if I look at this perspective shadow maps, it kind of looks very much like the camera view. And this is how I'm getting enough resolution for places that are close to the camera. So how does that work? It's really brilliant. I love this method. So this is an explanation of how it works for directional light sources. What perspective shadow maps, what this method is going to do is that it's going to compute the shadows in the canonical view volume. That's the brilliant part of it. So let's say that I have this directional light source, right? So if this is my world space, and this is showing the camera position. The camera is looking in one direction in the scene, and I have light coming from 3 different directions with directional light sources. If I apply my regular model view perspective projection and transform my points all the way to the canonical view volume, I'm going to get these trees deformed like this, the trees in the scene deformed like this. But also, my directional light source sort of deforms into a point light source. So my directional light source, if I apply perspective projection to this space, it turns into a point light source in this canonical view volume. So instead of trying to compute my shadow map in this space by generating some shadow map from the light source, I can try to compute shadow maps after I apply this perspective projection of my camera, original camera, of my scene camera. So in this canonical view volume of my camera, my directional light source turns into a point light source, and then I can compute the shadow map for this. So this becomes a funny transformation for the whole shadow mapping. I first transform everything to this canonical view volume of my camera, and then I transform them to the coordinate frame of this point light source that corresponds to this directional light source, and then all the shadows are computed. The shadow map is computed in this volume. This can also work, it doesn't only work for directional light, it also works for point lights, in which case point light sources can turn into a different type of point light sources or spotlight sources, or they can turn into directional light sources. But regardless, I'm doing the same concept here. I transform everything to the canonical view volume and compute the shadow maps in the canonical view volumes. Absolutely brilliant, and solves this shadow resolution problem really nicely. Although it has some difficulties. So there's a GPU Gem chapter on this. It's a very good one. So if you want to implement perspective shadow maps, I would recommend that you check this out. There are some practical problems with perspective shadow maps that one needs to deal with. Now, everything inside the canonical view volume would be fine. That will be fine. But if I have objects like this tree behind the camera that is outside of the canonical view volume, then things are going to be a little bit difficult. Things are going to be deforming in various ways, and computing the shadows for these, that's going to be a little difficult. So the standard, the typical perspective shadow maps method would struggle with this. Actually, stuff that is behind the camera will not cast any shadows, which is not good, right? Because I might have objects that are not visible to my camera, but still casting shadows. So like I'm seeing the shadow of an object, but not the object itself. That can happen, right? Very easily. And in those kind of situations, the perspective shadow maps would be a little difficult to work with. There are workarounds for this. There are ways to make that work. They involve changing the camera transformation a little bit. So you use a different kind of canonical view volume, try to include all the other objects inside that volume. So there are ways to get around it, but it becomes a little difficult to handle well. It's a brilliant method. I love it, but it has its problems. Because of that, what people often seem to prefer these days is a different variant of this perspective shadow maps type idea. It's a much simpler idea, actually. It's what's called cascaded shadow maps. This is, as I said, a much simpler idea. Now, here's what it does. Imagine that this is my camera. I'm looking at the scene. Well, I'm not visible when I do that. I'm looking at the scene from this camera view. All right. So what I'm going to do is I'm going to split this scene into multiple pieces using my view frustum. So starting with the near plane all the way to the far plane, I'm going to separate the scene into segments. So there's going to be a portion of the scene that's going to be the near part of the scene, the objects that are near the camera, and there's going to be objects that are far from the camera. Let's say that I'm splitting my scene into two pieces. Objects that are near, objects that are far. Now in world space, I can put a bounding box around these different segments. So the first segment, like I said, it's the near part of the scene. I can put a bounding box around it. And then the next segment is the far object. I can put another bounding box around it. And I can compute a shadow map for the near segment, another shadow map for the far segment. Right? And I can pick a different resolution for near and different resolution for far. Even if I use the same resolution, the near one is going to be representing a relatively smaller part of the scene. So my shadow map pixels are going to be distributed to a smaller part of the scene. Smaller part of the scene. That means that I'm going to have high resolution in camera space. And this way I can have shadow maps that can cover very, very, very large areas while having enough resolution for the parts of the scene that are close to the camera. So this seems to be the more preferred way of using shadow maps today. In like open scenes, let's say I have this directional light source that's, let's say it's the sunlight, right? Casting shadows on an open scene. Way out in the distance, you can see things that have shadows. For things like this, cascading shadow maps provides a very good solution. So for things that are far, far away, I could be using a low resolution shadow map, or I could be using a shadow map that's not necessarily low resolution, but sort of expands to a large area. And I'm going to have an additional shadow map for things that are close by. I can actually have multiple layers. I can have more than two layers. I don't have to have just one near and far. I can have near, medium, far, or I can have more than three as well. Depending on your scene, you may want to have more than three if you want to. And when I'm rendering, I am going to decide which shadow map to look at when I'm computing shadows. So depending on how far a point is from the camera, I'm going to determine which shadow map to use. Right, so if it's far, I'm going to be using the far shadow map. If it's close, I'm going to be using the close by shadow map. And that solves the problems with regular shadow maps, the resolution problem with the regular shadow maps. It also does not have the issues with perspective shadow maps. I mean, it doesn't provide as good a fit as perspective shadow maps, but it still provides a very, 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 very good fit. And also, it doesn't have the issues of perspective shadow maps, so this works out great, and this turns out to be the preferred method today when using shadow maps. Okay, so cascaded shadow maps, that's what it is. Let's move on to another way of computing shadows. Now, there are many, many methods for computing shadows. I'm thinking about all these different variants of shadow mapping as just shadow mapping, right? Different ways of using shadow mapping. But beyond these ray tracing and shadow mapping, there are actually many ways of computing shadows. I have no intention of going over all of them, but I'm going to talk about one more. I'm going to talk about shadow volumes. Now, this used to be a very popular technique for real-time shadow computation. It's not as popular today because shadow mapping seems to be more versatile, much easier to use. You'll see why. But I still want to go over this a little bit so that you've at least heard of this shadow volumes idea. It's actually brilliant. I love this. Now, imagine that I have this point light source, right? And I have some object in the scene. This object will be casting some shadow into the scene, right? So things that are behind this object will be in shadow, obviously. So if I have an object, another object that's inside this shadow volume, it's going to be in shadow. So the whole concept of this is tracking these shadow volumes and checking if the point that I'm shading is inside the shadow volume or not. That's what we're going to do. So given a point, I would like to be able to tell if it's inside a shadow volume or not. So here's how it works in practice. So I have my point light source here, and I'm going to show this in 2D. I have this object, let's say it's a plane, and there's a shadow volume behind this plane, right? I may have another object that is sort of partially inside this shadow volume. If that is the case, the shadow volume of this object will be intersecting with the shadow volume of the other object, right? So if I say there's no shadow outside, let's call it 0, I'm going to have a shadow +1 in this shadow volume. There's another shadow volume here. And then the intersection, I have two shadow volumes. Now, two shadow volumes are intersecting. And this can happen a lot in a scene, actually. And if I have another object like this, that's going to have its own shadow volume. And now I have even more of an intersection between shadow volumes. So how can I determine if a given point is inside any shadow volume at all? And they can be in one shadow volume, it can be in multiple shadow volumes. What I want to know is if it's in any shadow volume. So let's say that I have my camera over here and I'm rendering from this view. Let's concentrate on a single pixel, just one pixel of the image that I'm rendering. It's going to correspond to a particular direction. By looking at these shadow volume boundaries, just the boundaries of the shadow volume along this viewing direction for that pixel, I can actually count the boundaries and figure out if I'm inside any shadow volume or not. So in here, when I'm entering the first shadow volume, I incremented my shadow volume number by 1. And then I entered another one, it became 2, and entered another one, it became 3. And then I'm exiting one, exiting another one, exiting another one. So if I'm looking at a point that is back here, this point is not going to be in shadow because I went from +1, +2, +3 to +2, +1, and then 0, right? So it's not in shadow. So the way that this is going to work is that when I'm rendering my scene, I'm going to first render my scene and all of my objects without any shadows. And then I'm going to be rendering the boundaries of these shadow volumes. So the boundaries, the polygons forming the boundaries of my shadow volume. So let's start with this object first. I draw one of its boundary and then I draw its other boundary. And what I would like to find is that if I have a fragment over here that I've rendered, is this going to be in shadow, right? Now, here I would like to determine if it is inside this shadow volume or not. And I can determine that fairly easily just by looking at these boundaries. So over here, I had a boundary, its surface normal was in this direction, so I entered the boundary, and then I draw this polygon, its surface normal was in the direction that's, if you take the dot product of its surface normal and the view direction, that's going to be a positive number, right? So I can tell, all right, it's a back-facing shadow volume polygon. So I'm exiting a shadow volume. So I entered and then I exit. So all I got to do is that I will be rendering these shadow polygons from the camera's perspective. I'm just rendering these polygons onto my image, and they are automatically just forming these shadow volumes. And what I'm doing is that for each pixel, I'm counting how many times I enter a shadow volume and how many times I exit a shadow volume. So if I exited all of the shadow volumes that I've entered, the point is not going to be in shadow. If I haven't exited all of them, it is going to be in shadow. So basically, this is how it works. So if I have a scene like this and I'm trying to render this image, the way that I'm going to render it is I'm going to first render it without any shadows. There are different ways of implementing it, but regardless, I'm rendering these shadow volume polygons, and all I'm doing here while I'm rendering these shadow volume polygons is for each pixel, I'm counting how many times I enter and exit a shadow volume. So we typically use stencil buffers for that. It's just a way of counting something per pixel, and that tells you if you're inside if a pixel is inside a shadow volume or not. If it's 0, you'll know that I'm outside of any shadow volumes. If it's anything positive, you will know that you are inside a shadow volume. All right, so as I said, there are many ways of computing shadows, but the ones that we talked about today were just these three. We talked about ray trace shadows, we talked about shadow maps, and shadow volumes. Now, ray trace shadows, that would be the general way of computing shadows. Shadow maps would probably oftentimes give you much more efficient shadows, and they work with rasterization, so that's oftentimes the preferred method in real-time rendering today, but it only works for certain types of light sources. It can work for point lights and spotlights and directional lights. You won't be able to use them for area light sources that well. I mean, there are sort of ways of approximating shadows from area light sources using shadow maps, but they're not going to work so well. So, but shadow volumes, in comparison to shadow maps, they don't have the shadow map resolution problem. So shadow volumes actually give you really nice and crisp, perfect shadow edges, perfect shadow boundaries, perfectly hard shadow boundaries. But they have their own issues. I think we kind of need to generate all this geometry, deal with all that geometry. That's what makes them really not so attractive. So they're not necessarily efficient, especially when you have a lot of polygons in your scene. They can be kind of messy to deal with. And they also work with the same type of light sources. We can use them for point lights and spotlights and directional lights, but not typical area lights, for example. With ray trace shadows, there's really no limit. You can use them with any kind of object. Of course, the way we use ray trace shadows for different types of light sources, that's going to be different. So if I have an area light source, I am going to be sampling the area light source with, we typically use Monte Carlo sampling. We're going to talk about that stuff a little bit later on. We're going to be talking about how to use sort of ray tracing with different things. But the point that I'm trying to make here is that this is a general method that can, one way or another, handle all sorts of light sources we have in computer graphics. These are more specialized methods. Shadow volumes were one of the preferred methods back in the day. Today, we're almost exclusively using shadow maps. I'm not really seeing shadow volumes being used that much anymore. We're using shadow maps today for real-time rendering more than anything else. Actually, in real-time rendering, we started using ray trace shadows as well, because some GPUs do have ray tracing support, and shadow rays are relatively cheaper than other types of rays, so we can actually handle enough number of shadow rays for a lot of things. But if we have a point light source, a spotlight or directional light, shadow maps, or using cascaded shadow maps, for example, will probably give us a better performance in a lot of cases. Not necessarily, but in a lot of cases, in typical cases, I would expect to get a lot better performance with shadow maps as compared to ray trace shadows. So this would be an easier way of handling all sorts of shadows if you have the budget for it, but oftentimes we don't. Oftentimes we want to have something fast. Even in offline rendering, actually, even in offline rendering, shadow maps can be preferred. Shadow maps are still used even in offline rendering, and definitely for interactive rendering. Shadow maps are a preferred shadow computation method, and that's the one that we're going to talk about next time in detail. But as I said, it has its own limitations, that it can only be used for these types of light sources. But on top of that, it provides us good performance, which is what we want in interactive computer graphics, right? But I want to say one more thing. We talked about area lights, and I told you a paper that could compute lighting from area light sources. And that was great, but I said it does not include shadows. What do we do for shadows? What do we do if I have an area light for shadow? Well, I'm kind of stuck with ray tracing. There's actually a relatively recent paper on that very topic. It's brilliant work. I would recommend that you check it out. And the idea is relatively simple, and I'm just gonna talk about that. That's one of these things. By simple, I don't undermine it. Actually, I love it because it's simple. It's so elegant. So the way that it works is that we have this method for analytically computing illumination from area lights, including its attenuation and everything, properly at real time, and you can implement it on the GPU. It works just fine. So we can get this image at real time very easily without any problem. But the problem here is that there's no shadow. How do we handle shadows? Well, we're going to be using ray tracing for handling shadows. So this method is doing stochastic sampling for estimating the shadow. So you basically randomly pick some points on the light sources and send shadow rays. And you can implement it on the GPU today. And you trace these rays and you have some noisy shadow estimate, because that's what you would get with stochastic sampling, Monte Carlo sampling. And then we apply some denoising and you get a shadow image. And then what you do is that using this formula, you know the unshadowed illumination, you can estimate the shadow, and based on these two, you can estimate the shadowed illumination using area light sources. And this is what this paper talks about. It's fairly easy to do. You just compute the two and take the ratio, and you get this nice shadows where the light coming from the area light sources are computed analytically, and the shadows are sampled using ray tracing. So anyhow, this is not what we're going to be implementing, but I had to mention it because it's a wonderful paper. I love it, and I would recommend that you check it out. And this will also be a very, very good topic for a final project, if you're interested. All right, this is where I'm going to stop for today. As I said, next time we're going to dive into shadow mapping, and we're going to dissect it a little bit. We're going to talk about how to implement it. We're going to talk about all of its details and its problems and how we solve them. So it's going to be a low-level discussion of shadow mapping, because that's the method that we will be implementing for our upcoming project. All right, but this is where I'm going to end today's lecture. Thank you all, and I'll see you all next time on Thursday. Bye.